Namaste. Welcome to the lecture series on the subject Basic Thermodynamics. This is Module 5, Part 2, Real Gases. This is lecture number 12. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So the contents for this topic are compressibility factor, compressibility chart, reduced properties, law of corresponding states, and generalized compressibility chart. Okay, let us understand the compressibility factor and compressibility chart. So we know that the specific volume of the gas becomes very large at low pressure and high temperature. Therefore, it is not possible to conveniently represent the behavior of the real gases at low pressure and high temperature because of having high specific volume. You know that for a perfect gas, the equation of state is equal to PV is equal to RT. But for a real gas, so it doesn't obey this equation. So a correction factor has to be introduced to take into account the deviation from the perfect gas equation. So this factor is known as the compressibility factor Z and is defined as Z is equal to PV by RT. Here if Z is equal to 1, so then it becomes perfect gas. So for real gases, the value of Z is finite and it varies from minus to plus. That is, it may be less or more than unity depending on the temperature and pressure of the gas. Now let us study the reduced properties. So the real gases follow closely the ideal gas equation only at low pressure and high temperature. So at low pressure and high temperature, real gases obeys the ideal gas equation. But when I say low pressure and high temperature, so what is the basis for that? So here the pressure and temperatures are with respect to the critical pressure and critical temperature of the real gases. So I have to compare the pressure and the temperature with respect to critical pressure and critical temperature. So then I can say whether it is low or high, because a temperature which is low for one substance or gas cannot be a low temperature for the other gas. So let me explain by taking an example. If I take minus 100 degrees Celsius, which is usually all of us consider as a very low temperature, not just low, very low, and it's true also, this is low temperature for most of the gases, but not for air or nitrogen. Why? Because air or nitrogen can be treated as an ideal gas at this temperature and atmosphere pressure with an error which is less than 1%. The reason is this is because nitrogen is well over the critical temperature of minus 147 degrees Celsius. You see, the critical temperature of nitrogen itself is minus 147. So how can minus 100 becomes low temperature for nitrogen? It is not possible, right? So this is the minus 100 degrees Celsius is away from the saturation region also. So at this temperature and pressure, most of the substances would exist in solid phase, right? So usually in the negative minus 100, minus 147, so most of the substances will be in the solid phase. As the pressure and temperature of substance is high or low, you have to consider with respect to or in relative to the critical pressure and temperature. So with this example, so I am saying that minus 100 can be a low temperature for most of the gases, but not for nitrogen or air. This is because minus 147 degrees Celsius is the critical temperature for nitrogen. So minus 100 cannot be a low temperature for nitrogen. Okay. So all of us know that the gases behave differently at a pressure and at a given pressure and temperature, but they behave the same at temperatures and pressures normalized with respect to their critical temperatures and pressure. Because whenever I study the behavior of different gases, if I take the same pressure and temperature, so that is not the appropriate way to study, because whether pressure is or temperature, whether it is low or high, so that depends upon the critical pressure and critical temperature. So in that case, it is always better if you normalize these temperatures and pressure with respect to critical temperatures and pressures. So the ratio of the pressure, temperature and specific volume of a real gas corresponding to critical values, so they are called as the reduced properties. So you have the reduced pressure, reduced temperature and reduced volume. So reduced pressure is nothing but pressure by critical pressure, reduced temperature is nothing but temperature by critical temperature, and reduced specific volume is nothing but volume by critical volume. Now if you do this for all substances, and if you study the behavior of the gases, so then you can find that so they behave much to the same way. Okay. Now coming to the law of corresponding states, this law is used in the approximate determination of the properties of real gases when their properties at the critical state are known. According to this law, there is a functional relationship for all substances which can be expressed mathematically as VR is equal to function of PR and TR. So what is the meaning of this? From this law, it is clear that if any two gases have equal values of reduced pressure and reduced temperature, so they will have the same value of reduced volume. So that is what the meaning of this expression. So VR is a function of PR and TR. That means if any two gases are having equal values of reduced pressure and reduced temperature, so then they have the same value of the reduced volume. Okay. This law is most accurate in the vicinity of the critical point. So very close to. Now coming to the generalized compressibility chart, the compressibility factor for any gas is a function of only two properties, usually temperature and pressure, so that Z1 is function of TR and PR, critical reduced temperature and reduced pressure except near the critical point. This is the basis for the generalized compressibility chart. The generalized compressibility chart is plotted with Z versus PR for various values of TR. So this compressibility chart is plotted Z against Z is already studied, right? Z is equal to nothing but PV by RT. Okay, compressibility factor for various values of TR. This is constructed by plotting the known data of one or more gases and can be used for any gases. So this chart is already prepared and it is there in your data handbook, and it can be used for any gas. It is constructed for many gases. So this is the generalized compressibility chart. So you can see on x-axis you have the reduced pressure here, right? And on y-axis you have the reduced compressibility factor, that is Z is equal to PV by RT, and it is plotted for different temperatures. You see TR, reduced temperature ratios. Reduced temperature is nothing but T by Tc. So for different values of TR, so it is plotted starting from 1. So the bottommost curve, it is for 1, next 1.10, 1.20, 1.30, 1.50 and up to 2. Now here you can see it is plotted for different gases like methane, ethylene, ethane, propane, butane, all those things. So you can see all these points here. Means for a particular TR, this behaves almost same. Okay. So that I'll more about this chart. So I'll explain when I solve the problems using the compressibility chart. Okay. Now there are a few observations from this generalized compressibility chart. So it may be seen from the chart that the value of the compressibility factor at a critical state is about 0.25, and what the value of Z obtained from the van der Waals equation of state is 3 by 8, so which is higher than the actual value. So there are a few more observations from this chart. At very low pressure, so when I say very low pressure, so reduced pressure has to be far less than 1. So the gases behave as ideal gas regardless of temperature. So irrespective of the temperature, so all the gases behave as the ideal gas. At high temperature, where the reduced temperature TR is greater than 2, the ideal gas behavior can be assumed with good accuracy regardless of pressure except PR is far greater than 1. So at high temperature, so ideal gas behavior can be assumed with good accuracy, but it can be only up to PR is equal to 1 and bit above that. If the PR is far greater than 1, so then it is not possible. The deviation of a gas from the ideal gas behavior is greatest in the vicinity of the critical point. So this is we have studied in many times that the deviation is more near the critical point. The compressibility factor can also be obtained from the volume temperature or volume pressure data. Since the critical volume may not be consistent with the generalized chart, the pseudo-critical specific volume Vc dash is used in the definition of the reduced volume. So here Vc dash is nothing but RTC by Pc, and pseudo-reduced volume Vc dash is defined as Vr dash is equal to V by Vc dash. So here Vr dash, that is pseudo reduced volume, okay, is nothing but V by Vc dash, which is also equal to V into Pc by Rtc. That means V by Vc dash is there here. So in place of Vc dash, you have to substitute. Okay. So pseudo reduced volume, this is Vr dash. Vr dash is defined as Vr dash is equal to V by Vc dash. Okay. So with this I conclude the theory part of the real gases, and I solve few numericals on real gases in the next 2 lectures. Thank you.